Hello, and today, don't mind my crazy hair, we're going to be talking about Hubble's law and the expanding universe. I know I've touched upon this in other videos, but here we're going to get a little more into the mathematics of what Hubble discovered. And again, I know nothing, and this is my own interpretation of what I'm reading. So let us begin. All right. So this is an image of the Hubble telescope, Hubble's law and the expanding universe. I know nothing with E.M. Lees. So Hubble's law, Nala. My dog always loves to do this. Nala, you can't be in this video. Stop making noise, baby. Come on, Nala, come on. So Hubble's law, you're such a good dog. Hubble's law states the relation between the speed at which a galaxy recedes away from us in our present region of the universe and the distance of the galaxy means that its speed grows proportional to the distance. So again, think of an inverse, or every action is equal and opposite reaction, which would be a mathematical application of an inverse proportion. So speed over distance, distance over speed, think of it that way. For an example, the farther away a galaxy is from us, the faster it's going to move away from us. So the galaxy that's closer to us at the same time is going to be slower in its recession due to the attractive law of gravity. The attractive trait of gravity. So as the universe expands, all galaxies spread by the same factor. So at some point, our region of the universe will begin to move away faster at a speed proportional to its distance. So here we have v equals h0d, which is velocity equals Hubble speed by distance, or multiplied by distance, and the Hubble speed, based on his observations, comes to about 2.2 times 10 to the negative 18th power, s minus 1, so speed minus 1. It's, like I said again with the negative here, it always means that the way we measure it is by making it exceedingly small from what we ourselves are experiencing. That's how minute the distance is. But think about 2.2 times 10 to the negative 18th power. Considering that in the macrocosm of things, larger galaxies are moving away still at such a fast rate, even if it is in the negative 18th power. Hubble parameter. The universe is expanding, steady state theory, basically indicating that moving galaxies indicate entropy, the decomposition of matter, loss of energy as space-time stretches. So instead of things coming together, things are actually falling apart. But what happens to decomposing matter? Where does it go? How and when? It can't be simply created from the vacuum. The void or virtual particles, things that haven't come into manifestation yet. Think of the Heisenberg uncertainty principle, where once a particle has relayed its meaning or its speed, its velocity, its location, the system collapses. So what it cannot be simply created from the vacuum. So virtual particles, more so in the void, speak of what we do not know, what's yet to be manifested into reality. Distant galaxies are also more burnt out and irregularly shaped, slowly losing their equilibrium. Nala, why do you always do this? Come here, Nala. Stop being such a bad puppy. See, Nala's entropy, my puppy's entropy, for example, is that she always needs to cause trouble and make things fall apart when I'm doing my stuff. Stop it. And now she's stable because I called her over into the reality to stay in this region and stay in my gravity. And just stay here and be a good girl. Yes, you're such a good girl. So, anywho. So, galaxies are slowly losing what makes them basically stable, their equilibrium, and that is another example of entropy. So, as they decompose, as they move away, there's not a lot keeping them stable. And we can kind of see this through the cosmic background radiation, the sound of the Big Bang, which is uniformly spread more or less throughout the universe. So its expansion and tension is linear to us in space-time, that it's going forward and not going backward. Then we have our scale factor, which is actually a lot easier to understand, in my opinion, because it's basically D equals A times T. T is past time, the time that's passed. D is the rate of change in velocity, which equals time, which equals 1, less than 1 or greater than 1 by distance. And this more or less goes to critical mass, which we'll discuss in another video. But critical mass is basically stating how much matter is in the universe and what it says about the beginning of the universe and the end of our universe, whether our universe will continue to expand or dilute into a big crunch or collapse in on itself and result in another Big Bang. And right now we're more or less considered to be here at 1, meaning we're at perfect equilibrium. Nala! Stop it. Stop it, Nala. We're at perfect equilibrium. We're not going forward. We're not going backward. We're just expanding slowly, meaning our universe would be considered flat. Anywho, so velocity changes relative to the rate of how fast a scale factor changes. No delta, but we still need to be relative to the body in question, as everything we are observing is relative to our region of the universe and how close it is to us. And regardless of that, the Hubble parameter or constant is going to be constant in space, but the speed and rate of proportion can change depending on the distance by speed. Nala, stop it. She's so playful today. Redshifting, I know again we're talking about, I know in the last video redshifting had to do with more so the composition of gas in stars, but now we're also looking at it as light from other stars, other bodies, or nebulars that are traveling to us or away from us. The distance is stretching their wavelength, their light wavelength, and we can use this to kind of determine the distance. So light leaving a body equals time. Starting wavelength is, again, our factor here, our Lorentz factor. Expansion increase is 1 over a times t. Light is stretched by the same factor. What the? No. So Lorentz factor times 0 over another Lorentz factor equals 1 over a times t. Wavelength present by initial wavelengths over 1 times time found. So this is the translation of these equations. So particles in space-time, I can spare a moment, and I don't know why I wrote this down at the time. Nala. Stop it. I don't know why I wrote this down at the time, but whenever I thought of this, I'm thinking particles are more absolute than space-time. Space-time is a macrocosm, and its entropy is more or less visible to us, whereas particles are inconsistent in the way we perceive them. So that's why I wrote that down. I know this is kind of a confusing equation. So just think, wavelength is the present wavelength that we're observing over initial wavelength or the source equals 1 over time found. It is an inverse proportion. Inverse, equal and opposite reaction. Then we have our cosmological redshift, which is a fractioned permutation of wavelength. So z equals initial wavelength over minus y, initial source over the source. Wavelength present minus the initial source over the source. It's confusing again, but think of it again as an inverse. It's proportional. It's not a whole factor we're dealing with here. We're looking more at things that are relative as well as inverse, equal and opposite reaction. Redshift equals present over source equals 1 over time found. A fraction of time and inverse, as I said. And of course, the expansion of the universe. The expansion of the universe is an expansion of space, thus an expansion of space-time, not matter. Matter is stretched. It cannot be increased nor decreased. Energy is conserved, matter is recycled, but you can't create more from less and less from more. Distance beyond which galaxies move apart faster than the speed of light is called Hubble distance. The factor of space-time expanded before the Big Bang, and we're kind of still catching up. So we kind of see this as v equals c, or velocity equals speed of light. Distance, the Hubble distance, equals the speed of light over ho equals 14.x times 10 to the 9th power light years. Again, we're not going into negative. We're going into positive now because it's visibly seen. We can observe how fast light is. The Hubble distance equals speed over Hubble constant, 14.4 to the 9th power of the light year. Wow. 10 to the 9th power light years. A lot of distance we're covering. Stop it, Nala. Stop it. Be a good girl. Be a good girl. She's so silly. So silly. Particle horizon. I love talking about particles. The perceivable universe via light, matter that interacts with electromagnetic waves, is the distance horizon, which is 46 times 10 to the 9th power light years, which, like I said before, equals particle horizon. And again, it's visible. It's something expands that we can see. It's the initial stages of the universe as well, where we have a matter dominated with flatter geometry, which again is distance horizon equals 3 times the speed of light of time. is more or less or approximately equal to 42 times 10 to the ninth power light year. Again, we're dealing with such an expansive space and particles over that time. So we're getting an approximation here with the particle horizon equaling particle horizon over time, which equals speed of light over time times time. It's extremely difficult. And because of this, we are also seeing relativity, where galaxies curve space, and the curve tells us how fast a galaxy is moving as speed grows with distance. And I put in here dark energy, tension, and concepts of gravity because dark energy makes up 70% of our critical density in the universe. It makes up the flip side of matter, as energy and matter are interlinked. The tension of dark energy, instead of keeping things squished together, is pushing it apart. So think of it as like negative pressure finally. Yeah. Similar to the repulsive trait of gravity. And I believe that is it. Again, I apologize for my dog. Nala, come here so the people can see you. Come here, Nala. Come on. She just loves attention. Oh, yes, she does. Yeah, but she wanted to be part of the video, and she was playing with her baby. She has puppies in here. Anywho, so that is my take on the Hubble's law and the expanding universe. Again, I'm sorry this is kind of rushed. I'm actually dealing with 3 other projects for school right now, and that's why I didn't upload for the last 2 weeks. But I'm glad you joined me for today.